Hi guys. Um, so what I want to talk about in this video is the setup for how we do a chi-squared test for homogeneity. So I'm going to talk through all the different pieces for writing out the complete hypothesis test for this. If you need to see any of the pieces that I wrote down, just pause the video to see what I wrote, but I'll try and explain through every single one. So first thing we're going to do is we're going to work through phantoms is what again keeps us organized to make sure we have all the different pieces for a good hypothesis test. So to start off, there's a common theme throughout the chi-squared, the three tests, is we do not need a parameter here. We're going to use words when we do our actual hypothesis. So if we're using words instead of some sort of symbol or parameters there, we don't need to define what the parameters stand for. So our hypothesis, our null hypothesis, we're going to say the distribution between the samples is the same, and the alternative is the distribution between the samples is different. So this test is very similar to the goodness of fit test. The idea is in a goodness of fit test, you take a single sample and you're comparing whether that single sample matches up with a hypothesized distribution. So the common example that is used is a bag of M&Ms, and you see is the number of reds, blues, greens, whatever colors they have, doesn't match up with the distribution of however many M&Ms are supposed to be in every single bag of M&Ms. How homogeneity is different is you're still comparing distributions, but instead of comparing a single sample to a hypothetical distribution, you're instead comparing sample to another sample, and you can do even more than that. A sample compared to a sample compared to a sample compared to a sample. So you're comparing whether the distributions match each other rather than some hypothesized distribution. So you could have two samples, you could have more, but we're still doing categories with multiple types of categories in there. So again, the null, we're going to check whether the distribution is the same across the samples, and the alternative is whether things are different. For our assumptions, same first two, accomplishing the same task of independence there. We're making sure our samples are independent of each other through randomization. We're also making sure we're not too large by making sure we're less than 10% of the population. Now, you need to check this for every single sample. So if you have a sample of people from Europe compared to a sample of people from America, each of those individual samples need to be randomly selected, and each of those individual samples needs to be less than 10% of the population. The third assumption there is we're going to do an expected counts and make sure they're all at least 5. The expected counts here, it's a new way of how we're going to calculate this. It's super hard for me to explain it without a concrete example in front of me, but this is something you'll definitely want to pay attention to when I walk through an example. Because it's a thing that's often tested on, and it's pretty tough to do until you see it. We're going to name this test, so as long as our assumptions are met, that means we can now carry out the chi-squared test for homogeneity. The test statistic, exact same formula. It's on the AP formula sheet, which is pretty awesome as well. Chi-squared equals the summation of observed minus expected counts squared divided by the expected counts. The degrees of freedom, still going to calculate that, and we're going to do that with every single chi-square test statistic. The calculation for it is you're going to take the number of rows, subtract 1, and multiply it by the number of columns and subtract 1. Again, this is going to be a little bit confusing right now. We're dealing with a two-way table, so a table of data. You're going to take the number of rows in the table, subtract 1, the number of columns in the table, subtract 1, multiply these two together. Again, this is something that it's a little bit easier to see whenever I do an actual concrete example. Our last little bit for the chi-squared test for homogeneity, we're going to obtain a p-value. If you're going to do this by a graphing calculator, the calculator will tell you the p-value for you. If you're going to use the table, which again is provided to you in the AP exam, you can figure out a range of values that would be the p-value. Based on your p-value and how it compares to our significance level alpha, you're either going to reject the null hypothesis or you're going to fail to reject the null hypothesis. And again, if you're going to reject the null, that means you have sufficient evidence to prove the alternative. If you fail to reject the null, you're going to have insufficient evidence for the alternative. So a lot of similarities here between our other hypothesis tests we've done this year. A lot of similarities between this and goodness of fit. Just understand the key differences. A goodness of fit is a single sample versus a hypothetical um, distribution, whereas a homogeneity is going to take it a step further and it's going to compare samples to samples to samples. So where might you use this is what this is going to do is you might have a whole table of values that what we would have done is a two proportion z-test and compared a single category to a single category from another population. So we're comparing two samples, same category. What this is going to do is it can still compare across one sample to another, but instead of doing a single category, it could do multiple categories at the exact same time. Now, the reason you might want to do that is instead of trying to calculate a two proportion z-test and then do another two proportion z-test instead of doing another two proportion z-test, this does them all at the same time. So the reason why that's a good idea is if you do each of those individual two proportion z-tests, you have a chance for a type 1 and type 2 error every single time. So every single time you're doing a test, you're adding more of a chance to do a type 1 or type 2 error. Whereas if you do all of them at once in one complete type of test, that test for homogeneity, it kind of reduces that chance of a type 1 and a type 2 error. So that's kind of why we do that. Once we do this and we find out, hey, there is a difference here, then maybe we take it a step further and try and investigate where is that difference actually happening. Okay. So again, this is just a quick overview for the chi-square test for homogeneity. I will have a follow-up video that looks at a specific example on how to do one of these problems.